Hello, honors chemistry students. Welcome back. This will be the third and final notes installment of Unit 11 on acids and bases. This one will be about a topic called titrations. A titration is a fancy way of saying we're going to add an acid and a base together, but we're not just going to mix them together randomly. We're going to mix specific amounts together. And the idea behind it is if we don't, for example, if we don't know the concentration of a certain acid or base, we can use a known acid or base um, and add a certain volume of it, and we can do the math behind it. Because if we know the volume and we know the concentration of one, we can figure out the moles that were added. You learned in previous modules that when acids and bases react together, they react in a neutralization reaction, and we can actually write that reaction out. We can balance the reaction, which means we can get stoichiometric ratios, mole-to-mole ratios, that we can then use to figure out the unknown. The best way to go through it is just to show you, or arbitrarily or um, electronically show you here what a titration would look like. So if you were in class, we would set up a ring stand, right? And we'd have a clamp attached to that ring stand. And that clamp's purpose would be to hold a burette. All right. Now a burette is nothing more than a glorified graduated cylinder. It has markings. So it's got these graduation markings on it. Typically they're in milliliters. And you would be able to fill that burette. It's like a giant test tube with markings on it. You'd be able to fill it up with an acid or a base. Um, and we could measure then the volume of the acid or base in that burette. Now, what makes the burette useful is it's got this adapter called a stopcock on the bottom, and that stopcock has a valve that you can twist. And when you twist it, it allows the solution inside the burette to drip down out of the burette. And the usefulness of that is instead of just pouring it out of a test tube, we could actually physically watch. We could watch the volume drip out of that burette, right? So what we could do is we could say, say it started at 31.0 milliliters, and then we dripped out, and it ended at, 27.5 milliliters, right? We could say that 3.5 milliliters was added. So it allows us a very specific way of determining how much of an acid or a base we've added to our flask. Okay, so that's the first part of it. The second part is that inside the flask or whatever vessel you drip it into, you're going to have an acid or a base, the opposite of what's in the burette, and typically it would be like an unknown concentration. So what we could do then is we can use an indicator, and we'll go through this a little later, but if we put an indicator in there, as we start dripping the base into the acid in this case, okay, let's say that this is a base and this is an acid, right? As we start dripping it in, the pH of this system in here is going to go from low to high, right? So the pH is going to start to go from maybe 2 to 3 to 4 as we drip that base in. Eventually that pH is going to cross over the neutral into the basic region of the pH scale, okay? So if we pick an indicator that'll change color right when it's at the neutral point, then we can see it change color right when the acid and base stoichiometrically perfectly react with each other in their mole ratios. Okay, it might be a little confusing right now, but I will go through it with examples and hopefully it'll make it a little more clear. Okay, but overall, what we're talking about here is a titration. Okay, it's a neutralization reaction. It's carefully measured, and we call that a titration. Okay, titrations apply to things other than just acid-base reactions. We titrate tons of things in life. It's just a measuring. It's a way of controlled and measuring how much of one thing needs to be added to another. Okay. What we will use is we'll use a standard solution. Standard solutions are knowns. So we talk about the known in one of these two situations here. Either in the burette, we're going to have a known acid or base, or in the flask, we're going to have a known concentration acid or base. It doesn't matter. Either way will work. and we're going to use that to figure out the unknown. Okay, we will usually use an indicator or a pH meter to tell us when we get to that neutral point. Okay, because once the acid and base react 100% fully, they'll get to a neutral point. Now, what I want to show you here is what you would see, and I'll show you a video in just a second, but what you would see is you might, for example, let's say we have an acid, right? We have an acid in there with an indicator. And so right now, that particular indicator, and the one we typically use is phenolphthalein, that particular indicator is clear when it's in a pH of less than 7 or so, less than about 8. But when it's in an acidic solution, it's clear. Now, what would happen is what you're seeing here is we are dripping in what's called titrant, the stuff in the burette. We would drip it in, and I don't know if you could see, but where it drips in, it turns pink because right where that base, right, we would say that this is a base in the burette. The point where that base hits the solution, the base overtakes the acid in that small little portion of the solution. So it turns this pink color. But you would be swirling the solution, and as you do that, you would then mix that base throughout, and then you would see that those few drops would not be nearly enough moles of base to totally neutralize all the acid. Okay, so you keep dripping it in, dripping it in, dripping it in. What would happen is eventually the color would start to linger a little longer, and you would get to a point where the color would stay for a few seconds and go away. At that point, you would just switch to one drop at a time. And then eventually, when you put one drop in and you swirl it, that pink color would remain permanently. Okay. If it remains for about 15 to 20 seconds, we say that that is a perfect titration. You want to get the faintest pink color possible. And at that point, what we can do is we can look back up at our burette and we can then measure the volume in the burette. And that allows us to know how much volume of our titrant was put in. Okay. Now I want to show you a video of what that might look like. It's a really awesome video. But basically, right, you could swirl the flask or you can use a magnetic swirler like this is showing. But they would turn the stopcock, and at first you would drip pretty fast, drip, 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 and you would see the pink color start to form. And when you see the pink color, you can see it there start to form. You pull back on it, and as it stirs, as that base gets mixed around, the solution turns back clear. But eventually, you see here that with one or two drops, it stays pink. Okay, and at that point, we would know the titration is done. Okay, so that's the physical part of it. Where it gets a little trickier is doing the calculations. Now, before we do the calculations, I just want to talk about generally what you would see if you could track the pH of a solution while you're doing a titration. Okay, so if you notice here, right, if we were to start time 0, here's our time 0, or our volume of base added. So we're adding base. So base would be our titrant. We'll say sodium hydroxide. And we're going to add it into, it looks like hydrochloric acid. So we're adding a base to an acid. So what starts in the flask right here, where we start, is going to be an acid solution. So what you see is as we add drip, 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 the pH increases. Now, you would think that the pH would increase like this. You think it would increase linearly, but it doesn't. And it goes back to what we talked about when we learned about pH. pH is a logarithmic scale. It's an exponential function. So this does not react in a linear state. What it does, though, is the pH would gradually increase, gradually increase, gradually increase. And at this point right here in the titration, right about here, you would probably start to see that pink color linger a little bit. Okay. And so you would add a few more drops, right? Let's see, each one of those would be a drop, right? And then you'd add another drop and it would linger and you'd be swirling it and maybe it would last for a few seconds and then would go away. You'd add one more drop and it would last for maybe 5 or 6 seconds and it would go away. And then if you look at the thickness of this highlighter, right? One more drop would be enough base to shoot that pH way up. something kind of weird happens, is with about one drop, you typically get a huge change in pH. Okay, could be 4, 5, 6 pH values with one drop, which is why a titration works, because you can get within about one drop of perfect neutrality. All right. So if you look at where the titration curve spikes, and if you find the halfway point between that, we call that the equivalence point. Okay, we call that the equivalence point. There's another term called the endpoint. The endpoint would be simply where the pH would be where the pH would be, after you've let the titration go. Okay, so your endpoint might be a little higher than the equivalence point. That's not important. The equivalence point, right, is about halfway between those two. And you can see here that when we use this acid and the base, this is a strong base and a strong acid. Okay, you're going to get an equivalence point that's right at neutral, right at 7. Cool. So that's what a titration curve would look like. I want to point out that it doesn't have to be um, a base being added to an acid. You could start with a base in the flask and add acid to it, in which case you would start up here. And as you add the acid, the pH would drop down, and then it would fall down like that and level off that way. Okay? So you could definitely add acid to base, you could add base to acid. I'm going to show you in some subsequent graphics here, right, that the equivalence point will change based upon if we're going to use strong acids or weak acids or strong bases or weak bases. Okay, it's a very visual representation of what's happening, and I think if you really give a little time to it, I think it'll make sense to you. Okay, so the first one here, if you look, volume of base added. So this is a base. So we're adding base. So this is the exact same graph that we had on the previous slide. If you notice, right, we started a pH, a very low pH, which means it's a strong acid. And then we're ending at a very high pH, 13 or so, which makes it a strong base. So if you put strong acid and strong base, absolutely what you'd expect is that the equivalence point would be halfway between the two curves, and that equivalence point would be at 7. So you'd end up having a neutral solution, which is what makes sense. But it changes a little bit. Think about this graph. I can shift this graph a little bit. If you look, now we're doing a weak acid with a strong base. Notice the strong base still ends at that pH of 13 or so. But we're not starting down here anymore if we have a weak acid. The pH of a weak acid is not going to be 0 or 1. It's probably going to be more like 3 or 4. So now we're starting at 3 or 4, and then we're still shooting up to the same part. You can tell, right, that the total change in this graph is not nearly as large as the total change in the first one. Okay, so if you look at that visually, then if you look at the cutoff points, right, you got a cutoff point there and a cutoff point there. Halfway between them now would bring you a little bit above neutral, and so you'd have a pH greater than 7. Now there's a reason behind why the resulting solution is not neutral and why it's basic. We chose to not talk about those topics in the remote learning version of Unit 11, but trust me when I say there are ions that would be floating around in that solution that would cause it to be basic. And you certainly could do a little research on that. If you wanted to talk to your teacher about it, I'm sure your teacher would be happy to discuss that with you. But it's not something you need to necessarily understand why at this point, except for just a logical progression that if you start with a higher pH, the overall equivalence point should be a little higher. Okay, so the pH is greater than 7. We also, if you think about it, there's strong with strong and there's weak with strong. We can also do a strong acid with a weak base. Okay, so if you notice now, this would start low again, but the weak base would not get up to that 13 range. It would be a lot lower. So Now, if you think about, right, the cutoff points, and you find the equivalence point, now that's going to be a little bit below 7. It's going to be an acidic solution when it's done, okay? pH less than 7. And if you think about it, yeah, I've got a strong acid with a weak base. The strong acid is going to win out, okay? So it's going to be a little more acidic at the end. And then the last combination would be weak with weak. And take a second, right? Pause the video. Take a second and see if you could draw what that might look like. Okay, hopefully what you thought about is that if it's a weak acid, we're not going to start down here. We're going to start probably in the 3 to 4 range, right? And then we're going to slowly increase, and we're going to shoot up, and then our base is going to level off at probably like the 9 or 10 range. And if we do the cutoff for that guy, you see that our equivalence point is right around 7 again. Okay, so when you do a titration, there's one of 4 curves you can have when you're adding a base to acid. Notice they all take this general shape, right? They all start with a lower pH and it goes to a higher pH. They can do the full spectrum from low to very high, very low to very high. They can do the smaller spectrum, or they can do a shifted up towards the strong base, or shifted down towards the strong acid. Okay. I also want to point out that these are the 4 curves when you're adding base to acid. If we were adding acid to a base, keep in mind if you were adding acid to a base, it would look a little different. If we were starting with a base, we'd be starting up here. And as we add acid, the pH would go down and it would shoot down like that and level off. The same 4 situations would apply. You could have strong with strong, weak with weak, strong with weak, or weak with strong. You can have the same 4 situations. It's just the titration curve, right, gets flipped. So keep that in mind. There are 8 different types of titration curves you might be able to see when you do an acid-base titration. Right? In our class, we typically add base to the acid, so our titration curves are usually going to look like these. Okay. This is just a diagram. If you zoom in, you could read through it. It's just a diagram that's showing what the titration would look like. Okay. So now the important part is doing the calculations. So let's go through an example calculation, couple examples here. Understand that if you add acid to base, we can first of all write and balance the equation, and we can balance it and make sure we are able to do our stoichiometry. So we're dealing with HCl and NaOH. Those are the 2 most common acid-base combos we'll use in chemistry class. You'll see the nice thing about those is they're in a 1-to-1 ratio. If you have HCl reacting with NaOH, it's going to be a double replacement reaction, and you're going to see sodium chloride. That's the salt that you learned about in a previous module, and you're going to get water. And if you notice, 1H and then OH makes water perfectly. This is already balanced, so it's good to go. So understand now that this reacts in a 1-to-1 ratio. Okay, so 1 mole of HCl to 1 mole of NaOH, which is a fancy way of saying 1 mole of hydrogen ion to 1 mole of hydroxide ion, effectively. Okay. Find the moles of the standard solution that were used. So if you look at this, right, if you notice, it tells us the volume of the acid, but nothing else, and it tells us the volume and the molarity of the base, which means, right, in this example, HCl is going to be our unknown. We don't know the concentration. NaOH is going to be our known. We call that the standard. So you always start your calculations with the known substance. In this case, it's my base. Okay. So if I want to find moles, it's a very simple process. I rearrange my molarity equation. Molarity times liters. If you look back at the example, it says we used 0.15 molar. and we added 28.92 milliliters. Now, if you remember, molarity deals with moles per liter, so we need to make sure we put this into liters, 0.02892 liters. Okay, and we're going to do that calculation. So putting that in the calculator, you're going to see that it's going to react with 0.004338 moles, or not react with it, but that is the moles of our standard solution. So that's the moles of NaOH that were used. Okay. I'm not really going to round this yet. I'm still in the middle of a calculation. If you look, I'm going to have 3 sig figs in my answer. So I'm not going to round this to 0.004, as I'm going to lose significant figures. So keep your digits until the end. All right, find the stoichiometric equivalent number of moles. I'm going to show, this is a 1-to-1 ratio, which means it's very simple, but I want to show you the overall process so we don't skip steps. So in a standard problem, if it wasn't a 1-to-1 ratio, right, you would do stoichiometry. So you'd write what you have, you would set up your conversion, and you would say that 1 mole of HCl reacts with every 1 mole of NaOH. Now, just to reiterate, just to review, back to stoichiometry, these ones coming from the balanced equation. Okay, that's where those are coming from. Obviously, this seems kind of silly in this example because the math is kind of immaterial at this point. But that's how we do it. Setting it up factor label method so that our units cancel out. All right, so now what this is telling me is that I added 0.004338 moles of sodium hydroxide, which means it reacted with the same number of moles of hydrochloric acid that are in the flask. So I know then the moles of my HCl, and I know the volume that contain those moles. So I know the number of moles of HCl swimming around in the volume. If I know moles and volume, I'm able to calculate molarity, right? So molarity is going to be moles of the HCl over the volume, the liters of the HCl, and I now have both of those, right? So I can take this number and bring it down here, right? So 0.004338 moles of HCl all over the volume, if you remember from the problem, was 30 milliliters. So that's 0.030 liters, and I get 0.1446, which in terms of sig figs is 0.145 molar HCl. So what we've done here is we've used a titration to get a known volume. We've done stoichiometry to find the ratio, and then we've used that new moles to calculate the molarity of my unknown. Okay, and that process is what we do for every single one. You write a balanced equation, you figure out the ratio, you find the moles of your known, you do stoichiometry to find the moles of your unknown, and then you use that new value to figure out what is the missing value for your unknown substance. Okay, I want to do 2 more examples. I'm going to do them a little more quickly with less explanation because they follow the same protocols as before. Okay, so first of all, we have H2SO4 reacting with potassium hydroxide. So sulfuric acid reacting with potassium hydroxide, right? Undergo a double replacement reaction, you're going to get K2SO4, and that's going to make water. Now, if you look, this is not balanced, right? So we need to double our KOH. That gives you 2 Ks, right? SO4s are balanced then. Hydrogens are 2, hydrogens are 2. Hydrogens are 4 on the left, right? So we need to put a 2 there. So now this is balanced. If you look here, right, these two are reacting in a 1-to-2 ratio. So that's going to be part of my stoichiometry calculation. If you notice, right, these two are together. So I know the base. That's my known. My unknown is my sulfuric acid. Okay, so I'm going to find the moles of the known. And my known is going to be KOH. So I'm labeling it right here, so I'm not going to write KOH in all my calculations just to save a little time. But to find the moles, remember moles is molarity times liters. So my known was 0.5 molar, and it was 100 milliliters, so 0.1 liters. Okay, so that's 0.05 moles. Now, there are more sig figs. Since it's an exact number, it's exactly 0.05. I don't need to write them right now in my calculations. I'll make sure I round my sig figs at the end. All right, so now I'm going to use that. Okay, I'm going to do stoich. I'm going to stoich over to my unknown. My unknown being H2SO4. All right, so 0.05 moles of, I'm going to write my substance out, KOH. I'm going to do my conversion factor. From the balanced equation, 2 moles of KOH are required to react with every 1 mole of H2SO4, sulfuric acid. Okay, so now you do the fancy math, and you see that it's half the amount of sulfuric acid reacting, because it's a 1-to-2 ratio. We change the color on this guy just so it's obvious we're going between steps. So now take that down, and you can do the next step, which would be find the molarity of the unknown, which is H2SO4. Okay, so molarity is moles over liters. Be sure you use the correct moles. Okay, you are not using the known moles anymore. We have moved over to the world of the unknown. So make sure you're using the proper moles. So 0.025 moles over, and also, right, do not use 100 milliliters. That was for the known. This 45 milliliters, that's my unknown amount. So make sure that you are using the moles with the proper volume. Okay. So 0.025 divided by 0.045 ends up being 0.5 repeating. And in terms of sig figs, let's check my sig figs. There's 3, there's 4, there's 1. Okay, so unfortunately in this problem, the 1 sig fig limits me. So it's 0.6 molar H2SO4. Okay. So that's an example of a 2-to-1 ratio. Let's do one more. If you understand what's going on, you certainly could fast forward through this part, all the explanation, but I'm just going to do one more example for you that's also not a 1-to-1. It looks like we're reacting KOH with phosphoric acid. Okay. Here you're going to have K3PO4 because of the charges and water. All right. To balance this out, we're going to have to put a 3 there. Okay. And that's going to give me 3 oxygens, so I got to put a 3 there. 6 hydrogens and 6 hydrogens. We're good to go. So now we're balanced. Okay. So just like before, we're going to recognize that we've got a 3-to-1 ratio. So our stoichiometry is going to be important. Okay. So just like before, if I label the ones before, we'll call it step 1, step 2, step 3. I'm going to do the same 3 steps. Okay, step 1. Step 1, I'm going to find the moles of my known. If you notice, these two are grouped together. So my known here is the base, again. So moles is molarity times liters. 0.2 times 0.02405. It's going to give me 0.00481. which I could have done in my head, but I didn't even think about it. So that is moles of KOH. Let's use that value to do a little stoich, right? So 0.00481. If you're comfortable, you could just continue on afterwards. You could just continue on your calculation in one long run. I'm just breaking it down into steps to make it maybe easier for if you're still a little confused about it. Okay. Now I want to go from KOH, right? I want to go from moles of KOH to moles of phosphoric acid. And then I just look at the ratios. The ratios are 3 to 1. KOH gets a 3. Phosphoric acid gets a 1. So I'm going to divide by 3, and I'm going to get 0.001603, repeating, moles of H3PO4. So that's how many moles of acid are swimming around in that flask. They're swimming around in a certain volume, that volume being 24 milliliters. Okay, so I can then calculate my concentration by using my acid moles and by using my acid volume, 0.04 liters. Notice I'm not using, oh, sorry, not 0.04. I apologize. 0.024, 24 liters. Notice I'm not using that number again. I'm using the volume that deals with just the acid. Okay, so I'm going to go divide by 0.024, and it turns out my concentration is 0.0668. Let's look at sig figs. Looks like we can use 3 sig figs. So 0.0068 after that is a 0. So that's 0.0668 molar H3PO4. Okay. So I hope you can see that we did 3 example problems, and even though one was broken down quite extensively, we still balanced the equation, and then we did step 1, step 2, and step 3, which involved finding the moles of the known, then finding the stoichiometric ratio of the unknown, or amount of the unknown, and then figuring out what is missing with the unknown. So they're all the same steps. So that's the math behind titrations. Just to review, remember that a titration can form a titration curve when you track the pH. There are 4 different types of curves based on strong and weak being added together. And you can flip those curves if you're adding base to acid as opposed to acid to base. Okay, and then you always need to use an indicator to change color. So hopefully that makes sense to you. Obviously, if you have any questions, just like always, reach out to your classroom teacher, and hopefully those questions can get answered. Okay, all right, bye-bye.